second special lecture. As you know, we have 3 special lectures in the program by eminent women scientists, and you can learn, all these 3 lectures are named. The first lecture, the Bibha Chaudhary lecture, memorial lecture was first named. Then second, we started naming Bimla Bhutti Foundation after the support from Bhutti Foundation. And then we thought it would be also a good idea to honor and fondly remember one of the women scientists in India. So last year, this lecture was named after Rohini Godbole Memorial Lecture, and because she was a colleague and a mentor to many of us and whom we lost, unfortunately. Today we have a Rajeshwari Chatterjee Memorial Lecture. She was the first woman engineer from Karnataka and described herself as an engineer scientist. So we are very happy that for the Rajeshwari Chatterjee Memorial Lecture, we have Dr. Annapurni from Bangalore. She worked as a professor at IISc and later also as a chairperson of Department of Electrical Communication Engineer. She holds many firsts in her life, and it's a nice way to remember her work. Her work in microwave engineering is particularly known. So now I invite Professor Bhashwati Mukherjee to introduce today's speaker.
So, hi everybody. It's really a pleasure and privilege to introduce Professor Annapurni Subramaniam, who is probably one of the most eminent women scientists of India now. So she's the director of the Indian Institute of Astrophysics, and she was awarded the Rashtriya Vigyan Puraskar Vigyan Shri in 2024 for space science and technology. She has about 3 decades of research experience and has published around 200 research papers in topics such as star clusters, stellar populations, galaxies, and ultraviolet astronomy. She has trained a large number of students for projects, and she has guided 15 students for PhD, and several collaborated with her for thesis work. She was the chief editor of the Journal of Astrophysics and Astronomy, jointly published by the Indian Academy of Sciences and Astronomical Society of India during 2019 to 24. She is a scientific editor of Research in Astronomy and Astrophysics, which is a journal published by the Chinese Academy of Sciences. She heads the membership committee of the International Astronomical Union. She was involved in various space missions, including ASTROSAT, about which she'll tell you, and Aditya L1, about which you have also learned in your Astro course, the first lecture. The orbit of Aditya L1, rather. So she has contributed to the 30-meter telescope, TMT, which is being built by an international consortium with India as a partner. She is the principal investigator of the proposed next-generation ultraviolet optical space telescope, INSIST, leveraging on the experience gained from both ASTROSAT and the ultraviolet imaging telescope on board ASTROSAT. Annapurni has received many awards and fellowships. She's a fellow of the Indian Academy of Sciences, National Academy of Sciences. She's an INSA Woman Associate. She's a life member of the International Astronomical Union and Astronomical Society of India. She is a Kavli Frontiers of Science alumni, which is instituted by Kavli Foundation and National Academy of Sciences, USA. She's the recipient of C.V. Raman Young Scientist Award for Physical Sciences from the Karnataka government for the year 2018, recipient of Serb Power Fellowship 2021, recipient of Nasi Bhutti Foundation Lecture Award 2021. She's one of the top 100 women achievers of India as per India Today in December 2023. She's a Devi awardee. I may miss some of the awards that she has won. The list is very long. She received the Vanita Ratna 2023 award from the government of Kerala, and the NDTV Science Icon of the Year, Indian of the Year 2024 award. So as I mentioned already, her research interests are classical star clusters, classical B stars, young stellar objects, Bruce-Stagler stars, Magellanic clouds, nearby galaxies, and ultraviolet astronomy. So this is her as a scientist and as a science administrator, but Annapurni is also an accomplished accomplished violinist. So she gives performances, and so I think she inherited it from both her parents, who are all who are exponents of Carnatic music. Both your parents were vocal? Yeah, they were both vocalists, Carnatic vocalists. And so this is also very inspiring, particularly to this crowd, to see that somebody who is professionally so successful can also have another interest and pursue it when they're to the extent that they can give public performances. So I won't occupy the stage for much longer and invite Professor Annapurni Subramaniam to deliver today's talk.
I'm audible? Yeah, okay. So thank you for inviting me here to talk about, I thought I'll talk about a decade of ASTROSAT. So I have to explain a lot of things to you, but my name is Annapurni Subramaniam. I'm currently the director of Indian Institute of Astrophysics. And there are a lot of pictures over here. So I don't know how many of you have exposure to astronomy and astrophysics, but I know you have exposure to physics. So I'll take it up from that point of view. So I have to define a lot of things here, as I mentioned. A decade of ASTROSAT. Now, what is ASTROSAT? And why should we be talking about a decade of ASTROSAT, right? And so this is a picture of ASTROSAT. And this is a picture of a globular cluster taken by UV imaging telescope on ASTROSAT. And I think I have a pointer here, but but I'm so much used to walking around.
Yeah, okay, just.
Yeah, thanks. Yeah, so this is the picture. And this is the picture of ASTROSAT being launched on, kept over here, and launched on PSLV-C30 almost more than 10 years ago. And this is the logo of IAA. So now I will also talk about this cluster. So the point is the following. I have to defend the following. What is ASTROSAT? And why do you even need it? And why is it a big deal, right? And then why is it a big deal of being it there for 10 years? So I hope to defend all this and make sure that stop me and ask me questions if I don't make it clear whatever I wanted to do here. So before going to that, I would like to tell you about, so ASTROSAT, what is ASTROSAT? ASTROSAT is not a single telescope, it's more like a observatory, okay? So why is it an observatory? It's not a single telescope or a single instrument. There's multiple instruments on board this. So you call it as an observatory, right? And why do you need them? Why do you complicate it so much by putting in so many instruments out there? Why do you need this? That's question number one, right? And how do you achieve it? I mean, that's besides the question, like you have achieved it. That's what I'm trying to say. But let's start with saying that why do you even need it? And why is it a big deal, right? And why do you start off by putting all this? What are the initial plans like when you put them together? And why is it a space observatory? Why can't you just put it in the backyard of HBCSE here itself and observe, right? So these are the questions I would like to answer. Before that, I would like to also explain to you what an observatory is. How many of you have visited an observatory? Okay, just a few. Okay. So basically that means that you have visited some ground observatory. It could be radio observatory. You will be visiting GMRT, right? You have not visited yet. Yeah, so you'll be visiting GMRT. GMRT is an observatory on the ground. It's one, which I will not be covering in this talk because you will be going and visiting. But I'll be covering other observatories. I mean, I just wanted to tell you what a ground observatory would look like. What does it do? And you already have ground observatory, so why do you need a space observatory? And what is the focus? Okay? So let's move on. Let's first introduce me being the institute director. I must talk about the institute as well. But in the process, I will also take you through the journey of astronomy in the country as well as partly, and also about observatory because we actually set up and run observatories. So we start our journeys in 1786 when an observatory was set up in Madras. So that's one of the oldest observatory, one of the observatories set up in the country itself by Britishers then. Now, the requirement for an observatory in 1786 is completely different from the observatory as we see it today. Then, what are the requirements? First of all, there were no clocks. The clocks were the only at the observatories. Okay, time is kept by rising and setting of the sun or the stars, but there are no clocks. The clocks were there only at certain places. Now, there are also issues with what is your longitude. People want to tell you when, if there is a eclipse of sun event is going to occur, when there is only so some people had calculations. They didn't even know the longitude, because longitude is just a concept, right? Because you have a reference longitude and you have to estimate where you are. It's just a matter of time. The rising and setting of sun changes over the same latitude throughout the globe. So the only time difference, but nothing else changes. So the longitude, think about it, it's a very, very difficult concept to actually estimate longitude. So longitude estimations was a problem. Survey of India. Have you heard of Survey of India? We didn't know the map. We didn't have a proper map of India. So how do you even estimate distances, long distances? Height of the Everest. We didn't know anything. Height of the mountains. We had some idea, but not actual measurements. So many of them were carried out there. So observatory had different perspective then. They also counted stars, they also cataloged stars, apart from that. Then it started operating between 1792, it was set up in an observatory proper place, and 1899 it went to Kodaikanal. Now what happened in this 100 years, almost 100 years? There are several things, including discovery of helium, and of course Survey of India, longitude estimations, all those happened. You can read about it. It's a curiosity thing. If you're curious about it, go ahead. There's a lot of literature available. Go ahead and read up about it. Then the observatory moved to Kodaikanal, but that time you had branched out the Survey of India do the survey, the IMD do the meteorology department does the weather, and the Kodaikanal observatory started observing the sun. Now there was a famine in India, and then they didn't know why the reason was, and influence of the sun was understood to be strong, so they wanted to study the sun. That's how this observatory was set up. Then it became Institute of Astrophysics in 1971, and then where we are. So we did study sun a lot, and then we branched out to study stars and other things, etc. So that's how things evolved and made into bigger other things, etc. Now we have several observatories. So Kodaikanal Observatory is more than 125 years old. It's still functional. Have anybody been to Kodaikanal, gone to the observatory? Okay, at least 1-2 people. Okay, good. We also have an observatory in Kavalur, Vainu Observatory. It's in Vellore. And we have Ladakh, we have observatories. That's set up in 2000, because you don't see this monsoon clouds in Ladakh. So you have a year-round throughout the year observatory. And we have a radio observatory in Gauribidanur, and there's another center here. So these are the ground stations. We also have this UVIT Operation Center, which is part of ASTROSAT and IAA. And we also have Coronagraph, the VLC Payload Operation Center. And these two are space payloads. These happen in the last 10 to 15 years or so. We also are partner to the 30-meter telescope project. And we are also setting up two planetaria as well. So the ground observatories are there, the space observatories are there. So they've been there for a very long time. Now what are these observatories like, ground observatories like? Because you don't know and you have not seen, I'm just giving you some pictures. So this is the Kavalur Observatory is evergreen, it's in a Javad Hill forest. It's kind of an altitude of about 1,000 feet only. It's like Bangalore altitude, but it's a southern place. It's so you can cover the southern sky much, and it's established in 1960s. And this is a telescope I widely use for my PhD. So I used to spend a lot of time during my PhD time collecting data, because in those days, 90s, when you wanted to do observational astronomy, you need to use the data. Where will you get the data? You can't just download or anything. There's no internet. There's not even a computer is just coming around. So you have to go to the observatory. You have to stay there, collect the data. You have to get it in magnetic spool tapes. Those tapes, you have to read it, and there's only one machine which can read it and display, so you have to work there. So it's like that. Life is like that. So you have to go to the observatory, and otherwise you can't do astronomy. All that you can do astronomy is theoretical astronomy. You can sit in, you can't do a computer kind of evaluation, but you can do an analytical calculation in your book. That's the kind of work we could do then, okay. And if you want to submit a paper to an article, you have to type it out, everything in a Kaiwriter or something like that, or little typewriter, and then you have to post it. A European journal, or it takes a month to reach there, then the referee it has to be sent, so by the time you get a reply from the journal itself, it will take a few months. So things were different. Things were slower, things were much harder. Things we had to go to the observatory, go into the observatory, it will take time, and then you have to observe. You literally move the telescope or climb the ladder and observe through the night. So things were much difficult, and but it's fun. Like you're literally thrilled when you can see a star through the telescope or put the star through the slit and get the spectrum, and you see, oh wow. So that things were a bit different. So that's how I grew up. This is the observatory in Ladakh. Now this was established in 2000. It's already 25 years, and this is the top of the mountain. It's at 4,500 meters above sea level. It's almost half the height of Everest. You can see it's completely barren, so you don't have much of oxygen, and it's absolutely dry. So the conditions are quite severe, but the sky is good. Here on the ground of this, below this mountain is this Hagar Array, and this is the MACE telescope. These two are operated in collaboration with TIFR and BARC. So I have a small video to show you how the observatory in Ladakh looks like. Yeah, so this is the top of the mountain. This clouds actually will go and clear in the daytime. There's windy, but then after that it clears. This is the 2-meter telescope dome. This is the inside the telescope. This is remotely operated from Bangalore. So all the instruments are connected. You can actually choose which instrument you want to do, and so all of them are connected all the time. And there's a very compact dome. There's very little space for a person to walk. And this is an all-task system. If you know what it is, it just goes like this. And this is an instrument, special spectrograph in the ground floor. And this is another telescope which is operated with the IIT Bombay Growth India telescope. This is actually an automated telescope. This is the Hagar Array, which is a gamma ray. Actually, it actually detects gamma rays, but through optical only, not direct Cherenkov. So this is the major atmospheric Cherenkov experiment, MACE. And this is a very big telescope, which is 21 meter size and 356 meters. It's a PMT. And this area doesn't have any power grid. It is all through solar panels. And you can see large number of solar panels here. They're all connected. So this is a barren space, and this is the observatory. So observatory means you have a lot of telescopes. It will also have other facilities like power generation, if the coating has to be done, coating plants, and everything has to be operated. So it's not like you put one telescope and call it as an observatory. No, it doesn't work like that. So that's a ground observatory. And this one is multi-wavelength. The previous one which I showed you is a multi-wavelength because we have gamma ray telescopes as well as optical telescopes, and they cover from up to infrared. So optical, infrared, and gamma ray is there. And we are planning to extend it to sub-millimeter. You can talk to Bhashwati about that about it more. So it's a multi-wavelength ground-based observatory. Okay. Now this is a Kodaikanal observatory where they study the sun. I don't want to spend much time on it. The 100 years of data is used to study the long time variation of the sun. This lack of time I'm just skipping, but I can talk about it more if anyone is interested. This is the Gaurabidu radio observatory. You can see it's a low frequency radio. You can just see the picture of the antenna used here and compare with this shape of the antenna which you see in GMRT. They'll be different. So what it means is that the telescopes, the way it is constructed, the sensors, everything changes with respect to the energy of the photon you are collecting. So there's a huge amount of energy of the photon which is coming right from high energy to very low energy. But the way you have to design your experiment to collect it is different. So everything has its own challenges, its own technology to be developed. So just moving on. So why do we need a space telescope? So you already have all the wavelengths I showed you from gamma ray to here. Now why do you want to go to the space? The reason being the light is beyond the near ultraviolet. Everything is blocked. So you can't assume that none of the objects is emitting in high energy rays. So they are emitting. So you have to collect it. Now you can ask me, you said gamma ray you're collecting. How the heck, right? On the ground. That's that's a cascade, because Cherenkov, the cosmic ray, the gamma ray, actually triggers a shower, and you are collecting that shower. You're not actually directly detecting it. But ultraviolet and X-ray, you need to have the instrument up in space. This window you can collect it from ground. Again, this is infrared is blocked. Herschel, all those Spitzer, all this were in space. And radios, you can get it. But whatever you get, it will also have this turbulence of the atmosphere. So if you want to be the turbulence of the atmosphere, and you want to go to cover the entire wavelength range, then you have to have a space-based observatory. So what is the ideal situation? You can't put a huge telescope up in space because it's very expensive, and something goes wrong, you can't go and fix it. And launching is very expensive, and operating is also very expensive. So the ideal thing is, wherever you can, put it on the ground. But have instruments which you can launch up in space as well. So combination of instruments up in space and instruments on the ground is the ideal situation, because you need to sample all the photons to actually see what physics goes on in there. I'll also explain why do you need to sample everything. Can't you just take one part of the spectrum and understand it? It's like touching a part of an elephant and say defining the elephant. It's not possible. I'll explain that. So if you look at the sun, I hope you understand the black body radiation. And when the sun is yellow, which would mean that the temperature is, that is around where the peak of the radiation is, around the yellow wavelength, right? So that's how you see it. But if it is blue, then it is hotter, and it's red, it is cooler. Now, you can image the sun from ground in infrared and optical. It looks like this. But you can image the sun in UV and X-ray. It looks like this. Now, the temperature of this gas which is emitting is not on the surface, but it's outside, chromosphere and corona. So if you had not got these images, you would assume that this all it happens in the sun, which is not. Something else is happening, and you need to understand what this is, why this is so. And this is very important because sun holds the corona, which is 1,000,000 degree Kelvin. We don't know why the heck that is that temperature, right? So if you want to study the corona, you need to have these instruments, and you need to have them up in space. So there is a requirement, even to understand the sun. Even if we had 125 years of Kodaikanal data, it is not possible, right? So that is a requirement. Now, if you go to outside that, you see galaxies. You have the cold gas which is emitting in the radio wavelength, and the very hot gas emitting in the X-ray. So if you want to understand the entire, so galaxy will have all the ecosystem there. It's cold gas to hot gas to all sorts of physics happening there. So if you want to isolate yourself to only one wavelength, then you will be probing only that physics. But that physics is, you're sitting in the environment of this room, right? You can't say that I'll study only one part of it, which is not isolated, which is actually integrated into the system. So you have to have an integrated view of the galaxy, which you would need, you have to sample in all wavelengths. So I hope I established that you need to have sampling in all the wavelengths to study the ecosystem, because everything is out there happening, and it's not isolated. One process can affect the other. So if you don't sample that, the other one is not, you're not studied it or understood it properly. So that's a requirement. So in the world, what does it happen? You have a combination of, as I said, this is not this international case. So these are all international multi-wavelength observatories up in space in combination with ground-based observatories. So this combination gives you a full coverage of gamma ray to radio. Then you can actually combine the data from everything and then do it. Now, how do you do this? Do every instrument looks at the same object at the same time? Not necessary. If you're looking at an eruptive or a transient event, then everything has to look at it at the same time. But things are not transient and it takes a long time to do, then you can actually sample it multiple times. Like there, you would have talked about astronomical time scale, right? Things don't change at all. There are objects, but there are also objects which change in seconds time and things like that. So they are very transient events. Supernova explosion, or even a coronal mass ejection of sun, etc., accretion event in a black hole. Those are very, very small time scale changing events where you need to combine everything. So there are cases where you need absolutely simultaneous data coverage for the entire wavelength. But in some cases, no, you can just get the data, taken over a spread of time, it's fine. But the requirement of the multi-wavelength is important. Then, do we have such a thing? That is what partly met by ASTROSAT. Because it covers from about 200 keV X-ray, so 100 keV CZTI, to visible coming from UVIT. So this is a large X-ray to hard X-ray to soft X-ray to UV, far UV to optical it is covered. The rest of it, infrared we don't have it in the observatory, but we have optical in the ground, radio in the ground. So ground data is there and some amount of thing is covered here. Now the only thing is the requirement of ASTROSAT is that, since I mentioned that if there is something variable, this cannot see the sun for that matter. This is not designed to study the sun. It is designed to look at the dark part of the sky. So in the dark part of the sky, you can look at AGNs, it could look at galaxies, it could look at stars, clusters, etc. But all these instruments together will see one point. Like I mentioned, simultaneous. So even if you don't need simultaneous, it doesn't matter, it will collect the data for you. But there are requirements for simultaneity, so that will give you simultaneous requirements. So simultaneous data. So the idea is to have a large time frame of simultaneous data so that you can see what is the physics going on here, which is affecting the high energy range. So this is a small video of how the UVIT was made. So I want to, so these are the 5 telescopes, and I will be focusing on ultraviolet imaging telescope because I was a calibration scientist on this, and these are the 2 windows here. So it's a very massive thing. Actually, the whole thing will come something like this, because we have the UVIT itself sitting there this big. So the entire thing will be something like this. It's a very big, and it has been orbiting for the last more than 15 years. What do you mean by orbiting? I don't have a slide for it, but I can explain. I think you already have one. So this is a low Earth orbit, like a Hubble Space Telescope. It is about 650 kilometers, and one orbit will be 90 minutes. And so what happens is, it passes over Bangalore every once in 90 minutes. So you can have every 90 minutes passes through, you download the data, you also uplink all the commands. And that's how it does. And so making of UVIT, it's been difficult for the reason that, why is this? So now I explained that this is an observatory which is required because you need multivalent data. Now these are done for the first time in India. I mean, I think the LAXPC, X60 and CZTA were all, TIFR was leading those 3. They had X-ray heritage. UVIT was led by IIA with IUCA and other institutions. TIFR was also part of it. We have not made any UV telescope before, space telescope before. So what is the challenge? Is that it has to stay alive through the launch. And then all the electronics have to be alive when it is operating. So nothing should go bad. You don't have a backup. Some things have backup, not all will have backup. So nothing should break during the launch, and no electronics should go bad. Then only everything will work. So everything worked. Some of them failed after a few years. Like one of the LAXPC failed, and one of the detectors of UVIT is not working in UV. But far UV is working. So like that, but at the launch and after for first few years of operation, everything was working properly. Now the challenges are that as I mentioned, this absorption takes place, right? Why does it absorb? Why is the atmosphere absorbing that? Anyone? This transparency the opacity is 100%. That means transparency is 0, right? So why is it stopping? What is stopping the high energy radiation from reaching the Earth? Everybody is sleeping. No, what is this? What are the? Why do we? I mean, it's also linked to why do we have life sustained on the surface of the Earth, right? Ah, okay. So those. That's the right question. So ozone absorbs the molecular absorption. That is what mostly happens here. So molecular absorption happens in the ultraviolet and the X-rays as well. So you can't have contamination. So how do you build such an instrument? If in the room, if I shine an ultraviolet light, it wouldn't reach the detector because it gets absorbed in between. So how do you even test it in a laboratory? You need to have a clean environment. And also, the entire system of the telescope should not be, of course it will be heated up because it will be facing the sun. And during the heating, it can also start emitting some molecules within the paint or whatever it has, right? It should not emit. So you have to not only make it, but also sustain it in space and also make it sensitive. Sensitivity should not vary. How do I go and measure the sensitivity? I have to keep measuring the sensitivity and make sure that it doesn't, or the overall variation, I understand the overall variation. But before let it vary, you have to make sure that all the precautions are taken that it doesn't vary with all these emissions, etc. So my job was to calculate the performance and make sure that, find a method to characterize in space. That was my job. So because of this, your system, your laboratory where you're making all of the instruments in ASTROSAT should not have molecular contamination. So we never had any lab like that. So we had to learn not only setting it up, but run it. When people go, we also are contaminators. When you take things, you're contaminating it. If you're taking a part into it, a nut or bolt or anything, you have to bake it. So baking procedures. And how do you know your lab is not having contamination? So you have to actually measure the contamination, you set up everything. So we've been doing it for the last 20 years or so. And if something happens, how do you take care of it? So all those things that we learned. So these are all part of, not actually you don't know, you only know that something is delivered and it's working, but they're all part of the homework and the groundwork you need to do and invest in it. People, commitment over the long period of time. So that's why I wanted to show this movie, which actually says how this is done. This is done by our engineering team for 10 years of UVIT. So this is a collaboration. I think I'll just skip the first few. Yeah, this is starting from here. So this is this MGK Space Laboratory. It was established for that. And these pictures are in, you can see the 2013, 14, etc. So PPEs were used then itself because we thought which people can't go in. And this is the cleaning process of the tubes, ultrasonic cleaning for all these components. And the baffles, their coatings, anodized coatings are also separate because they cannot emitting any UV. And contamination check with an UV lamp. And so these are the kind of checks we were doing. And these are baking chambers where you put it and heat it up for a certain time. Everything goes in. You can see cables being baked. And so these are detector modules. Everything has to be vibrated because when you launch it, so this is inside the detector. So many components are there. So actually in one of the one of the vibration thing, everything fell apart. Then we had to literally bond everything together. So heaters, and because this thermistors, you need to measure the temperature to make sure that it is same temperature, because if the temperature is not maintained, the PSF will go away. So all this is the making of it. So these are collimator telescope to check the telescope. This is not part of the delivery, but you need to have such systems. We only designed and made everything. These are the mirrors, the cell, which is bonded together and tested now. So all the testing equipments we had to make, testing methods you need to make, test reports you need to make, and make sure that it is all valid. So this is the secondary with the baffle assembly. Now people are integrating into it. Very, very time consuming and very, very focused, because if you have to turn a screw by 45 degree, you can turn only by 45 degree. If you turn more, it will break, turn less, it will be loose. So you have to be very, very focused. So this is in 2012. And this is a far UV telescope, NUV telescopes. There are two telescopes. The reason being far UV has to be reflective. So this is the one. The back end is the instruments are sitting here, detectors are sitting here. And it is going into the vacuum tank for calibration, because that is where no molecules are there. And after that, two of them. This is the flange and integration. This is high voltage devices, and along with that the computer, detector, all the wires, everything will go. And this is the class 100 assembled one, and these wires are purging a dry nitrogen to flush out. As I mentioned, if the molecules are there, what will you do? You flush it out. You can't go and take it out, you just flush it out. So dry nitrogen purging. These are handling transportation containers, and while moving from one place to the other by truck, it has to be floating. It should not get any jerks. And we also measure the acceleration. You should not, so this is the special transportation trucks. This is the entire view of the lab. Yeah. Yeah, so the shaking and baking at eyesight. Here also we had to strictly bring in contamination because there were particle contaminations there. And this is the integrated system. This is the checkout. Again, purging is going on here. This is the whole thing together before launch. And the transport of ASTROSAT to the launch site, the entire thing has to go very, very carefully. And then the launch on 28th September 2015 actually. Yeah. 1 second. Just 1 second, yeah. Yeah.
The kind of things that you maintained at the laboratory, the vacuum, the levels, they were similarly maintained at ISRO, because if you want to do another.
Yeah, so once it is there, what happens is this is sealed. So this is sealed, but there is a seal which you have to open the doors. So you can see this particular thing here. These are the sealed ones and stuck, and these are open in orbit after launching. So they are all closed.
So once you make the checks at the laboratory at MGK method, you did not open
No, you can't open it, but purging is there. But while integration, so this is the spacecraft being, so this is the instrument being integrated. This is a checkout at ISRO site. Then it is integrated with the space thing, entire the spacecraft, all the communication devices. That's what is going on here, checkout, because you assume that this is an independent thing and you are communicating with it. After that, it has to be put inside the rocket. And before that, that rocket which is going to fly in the orbit will have fuel. So first it will be taken and then put it in a case, and then the fuel has to be done. So refueling will take place in the one side. So we used to go there and take turns to make sure that everything is in place and all that. Then it will be integrated to the rocket. That time they will be cutting off this. They will not let have. So last some 48 hours to 36 hours, we did not have any purging. We had to keep our fingers crossed that there's no contamination there. Then it flies. Yeah, but this was opened 2 months after that. So even everything had this problem, but since everything was starting on, there would be outgassing. So UVIT was started 2 months after launch, opened. So everything opened so that this door is still closed, so it goes away, and then you open it finally. And there are also ram angle clearances are all there, so precautions, a lot of precautions. So I'll just go through quickly. So I was giving the last talk, I just pulling out my Excel sheet, the plan for which is the object which will observe on 30th first. So this is the table which I was making, which filter will go, which mode, and commanding for that. So this is from my Excel sheet for the first window. So this is the observation started, and first you get the integration done. What happens is you will get these trails, because this satellite is drifting. You have to do the drift correction. So all these corrections, because the drift correction will be, the 3 channels will give you 3 different pictures, because the detectors are turned and one is reflected. So you have to correct for all this. So what I'm saying is the data comes, the raw data comes, will not be in any useful form. You'll have to make a lot of corrections, and that requires understanding the instrument. So the instrument has to be understood. Then we had quick look which found that, okay, everything is fine, working fine, and this is how it is done. And we have been tracking the sensitivity, and the latest paper of 9 years of data shows no change in reflectivity, and so this is the initial 3 years. So we are fine, it's working very well. No change in sensitivity also, because all these precautions are taken. The data is public, anybody can download it from ISSDC. This is the old website, now Pradhan is there, you can download it from Pradhan also. And these are the kind of objects which I studied, and yeah, so I'll just go through quickly about what I have studied, because there's not much of time left, I guess. How much time I have? 10 minutes? Okay, fine. So are you both want to take a break? Any questions at this time? So I'm moving to science now. So on this instrument, if you have any questions, that will be a break and give you a wake-up time, right? So any questions? Yeah.
So you mentioned that LAX, AC, and UVIT has failed. What is the reason
Yeah, so the UV has 3 channels: far UV, near UV, and visual. One telescope is far UV and the other telescope is near UV and visual. The near UV and far UV has, they are, okay, so what I have not told you is that they are all photon counting modes. So you can detect the, you can make an image in multiple ways. Now if you have plenty of photons, like the one from your camera, you integrate, like you give 1 second of integration or 2 seconds of integration. It's like buckets. Right? You get the bucket and convert all the photons into electrons, and you measure how much it is the voltage there, and you convert that voltage into something, and convert the analog to digital. Do you know how the camera works? Curious about it? Go and find out. It's very interesting. Now, if you want to take this camera and find something which is very, 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 very dim, how do you do this? You have a lot of photons. That's why it's bright, isn't it? When the photon is like you have some 1,000 or 1 million photons coming in sometime, you don't mind if you miss any photons, doesn't matter. You have enough photons coming up. But you say you have only 1 photon coming in 1 minute or 2 minutes or even 10 minutes. How do you, that photon is precious to you. That's what happens in high energy. You can't miss it. So how do you make sure that once the photon enters, you have to make a bang saying that yes, it entered, right? Then only you'll say that yeah, I found it. So how do you make it bang? By exaggerating it. You can use a photomultiplier tube. That's what it does, right? You hit a photon, then it amplifies it into a shower, and then you detect the shower. That's how it works. And you don't mind because you are not getting so many. You can't have a shower for 1,000 or million photons because it'll be flooded. It'll destroy. So you can't have it. So you make sure that you count every photon by making sure that the photon releases a certain shower, and you collect the shower. So that's a photon detection technique. That is how high energy detections happen, because there are only few and you can't miss them. But in optical, it doesn't matter. You have plenty of it anyway. So integration works. So here you have a shower. That's how the things work. And these require high voltages because it's a photomultiplier tube. It requires high voltages because that has to be accelerated. Now, these voltage devices you have a cosmic ray particles in the cosmic ray showers also happen in space, and you need to actually take the thing out. There could be static. It could be you have to take it out. Sometimes you can't. So you see in the detector some variations from observation to observation. So then you understand that there's something wrong with the detector. The only thing is to switch it off and switch it on, and that's a risk in space. But you have to do it. So we have to do it at regular intervals to make sure that you don't have any added charge particles sitting there and meddling up with the radar system. One such operation, we could not bring the near UV back. We again signal it and bring it back, it doesn't work. In the case of lax species, the mechanism is different. You have a gas and you have a proportional counter. So that kind of a shower, it detects it. There's a leakage of the gas. So there, one of the detectors lost because the leakage, and they could not maintain the pressure, and because of that, you can't calibrate it. So that is also, that's the reason two things go.
Also for purging, do we use only dry energy and nothing else?
Dry energy is what is generally used, nothing else as such, as if I know, yeah. That's in the ground, not in space, yeah, before lunch. Yeah. We'll restrict the question to 3 or 4 because then otherwise we'll eat up the thing. Yeah.
Hello. Ma'am, so when we send this observatory to space, how do we test that all the sensors and all the payloads that we have will be able to withstand the atmosphere and the radiation at space? Like, how will we test for that? Good question.
So we do have like basically you're looking at detectors. So the rest of it is like should not get broken, and they should not be misplaced. Like if it's an optics and the angle or support it breaks, then obviously the angle changes and you won't get the focus. So how do you make sure that this work in space is you simulate it everything. So not simulate, actually make it go through this environment while in ground. So it's called environment testing. So in the case of ASTROSAT, we have qualification model, we have full engineering model, which has to go through all the shake and bake. Shake means you shake the entire instrument you have an adapter and then shake it to the extent that how a normal rocket will shake. So people know how many G will have in which direction. You have to shake it and make sure that all the bolts, nuts and everything are in place. Nothing changes. So you have to take it back from the vibration test and go through a functional test. There is a list of things you need to do. And it has to pass all the functional tests. If something is not passed, then you have to take it back, redesign it, redo it, and again test it. So after passing everything only, it is done. In the case of detectors, harsh environment, there is a radiation hardening also happens. So only after radiation hardening, the detectors are taken. All precautions are taken as much as possible.
Thank you.
Any urgent question? Otherwise, we'll move on. Yeah.
How many years
Can you? It's okay. Yeah.
Ma'am, how many years this project took, like from an idea to launching into the space? How much time?
Yeah, it's a very long time. So I think it's somewhere in the middle of 90s is when they started doing it. But I understand that somewhere around 2002, 2003, the project got approved and the funding came. And then also the infrastructure had to be made, because without the infrastructure, we didn't have any MGK Menon lab by then. So we constructed the MGK Menon lab. So I got into the project by about 2006 or 5. I think. And then we actually completed in 2013, but final vibration, the visual detector, the bonding came off. So we had to take the entire thing back into the system and then go through tests and do everything, and then delivered in 2014 and launched in 2015. Yeah. Okay, so let's move on with science. So this is the type of science observed by various teams, and generally these are done. So I work on clusters. So star clusters are a group of stars, which can be, these are kind of, they're called open clusters because there's no specified figure you can imagine. It's open. So then they're not closed kind of a thing, but these are like balls, so they are globular clusters, they're called. And their numbers are small, and they're also younger stars, and they're found in the disk of the galaxy. This one is actually much larger in number, and they're mostly found in the halo of our galaxy. But that's only true in our galaxy. If you go to other galaxies, it could be different. But the main thing is the number is small, and many could be younger stars. Massive stars are found. But here they are all, what do you mean by massive and low massive? What is your benchmark? My benchmark is the sun. So sun is 4.5 billion years old. So I would consider low mass stars as massive less than the sun, and they would have lived longer. So you also say that, what do you mean? The smaller stars live longer and the massive stars live shorter. Why? You expect more fuel in massive stars, right? So they should live longer, isn't it? And the small mass stars have less fuel, so you should burn out fast. Yes or no? It's counterintuitive when I say that low mass stars with less fuel live longer and massive stars with a lot of fuel burn out fast, isn't it? Do you understand the difference? Some of you. Some of you have the question, raise your hand. I can explain in 1 minute. Or you want to find out by yourself. Oh, come on, please tell me something.
They know this.
You know this?
I think they're shy to say that. They know this has been done.
This has been told to you, right? Okay, fine. Right. So I understand that. So this live a very long time. So in our galaxy, these are like 10 to 12 billion years old. So these are important. Why should you study them, right? The next question is, they are look like, massive stars. You can study them, and young intermediate stars, etc. These are very old stars. So you can study how the stars evolve as a function of mass. Point number 1. But these are also very large number of stars confined to a smaller space. And what is the kind of orbit they go? They all like go around with the center of mass. That's the orbit they take. They are not stationary. Nothing is stationary in none of the objects are stationary in space. They all go around the gravitational potential, the gravitational center. Here, the gravitational center is somewhere nearby in the central. So they have to go with respect to that mass. So the entire potential they see, and they move. So that's chaotic orbit, and they end up colliding. In fact, they end up colliding. So that's the only system in the universe where stars actually collide. So they also produce some exotic objects. And they are more or less near the center, and this crowded picture, you cannot see where it is. You can't see the exotic stars which are in the center. That's one of the important things which globular cluster needs study. The other one, open clusters, basically try to give us understanding of how the stars evolve. Now you can ask why, I'll explain. So like these are the, do you know what a Kalamainty diagram is? We'll explain to you, right? So you actually have only two, all that you get is a photon. It could be from whichever energy it is, right? Now how can you measure for the various types of stars? What is the property you can measure? You can measure the brightness and temperature. Temperature from, you can actually, you don't need a spectrum, but you can sample the spectrum in 2 different points, and the ratio of the flux will tell you the temperature, right? That will give you the slope of the spectrum. So that's the temperature. So you can actually put the temperature on the x-axis and luminosity on the y-axis. That will give you the luminous and the hot stars. So these are the diagrams. So what happens is the massive stars, these are magnitude, sorry for this confusion here, but these are bright stars, these are also hot. So in a Kalamainty diagram or in a HR diagram, this end is luminous and hot. The luminosity is in such a way that the faint is here and the luminous is here. The magnitude scale is ulta. So this is bright and hot. This is faint and cool. This is bright and cool. This is faint and hot. These corners are important because this you need. So you understand the 4 pi r square t raised to 4th, which is giving you the luminosity. Luminosity goes as temperature 4th and radius square. So if something is hot, it has to be here. This is hot and this is cold. An object is hot. Now you want to know whether it is luminous or not. That will depend on its radius, right? Because this is hot. This is here means its radius is large. It is hot and large. This is hot and small, which would be white dwarfs. White dwarfs is tiny. Radius is very small. So they're hot, but they're small. Here they're cool, but here they're bright. They're giants. They're cool but giants because their radius is very large. So 4 pi r square makes them here. This is hot because t raised to 4th. That's how it varies. That's why this diagram is important. Once you know where they're located, you can actually see what type of a star it is, what is the nuclear reactions is going through, why the way it is. Okay? So the star clusters now populate most of the diagram. Here you have white dwarfs as well in some clusters. So they populate most of the places. So since you have all the evolutionary phases coming in a cluster, you can probe them as a function of mass, as a function of age. So that's the beauty of it. All right? So exactly what I meant. As the cluster ages from 100 million years to 1 gigayear or the 10 gigayear or globular cluster, it actually encompasses, goes to the entire Kalamainty diagram or the HR diagram. So you can actually understand, depending upon what age, you can actually understand the stellar evolution. And how do you understand it? By making models. You make models and compare with observations. That's how it does. Now why do I care about these stars? So as I mentioned, these are the white dwarfs. They're hot and luminous. So it's like 10 raised to minus 4. So it is quite less luminous, but they're hot. So if you want to study something is hot, then you have to pick up the short wavelength. So ultraviolet, if I take if you take a picture in UV, these parts will be visible more. These will not be no flux will come from here. So if you take a case of this, most of the stars are cold. So nothing will appear bright. Only this one will appear bright. So in a crowded globular cluster where most of the stars are emitting in visible and infrared, you want to pick out only the hot stars. UV is the best one because it's like switching off all the stars. So that is how we used for globular cluster. So similarly, if you look at a globular cluster of the same NGC 288 in optical, you can see the crowding. It's almost similar scale. You can see these 3 stars out there. It's the same scale. It's in far UV, the same cluster in far UV. See how crowding is lifted. you can pick out the hot stars. And they are produced by not sometimes different evolutionary theory, because it's not single stellar evolution. There may be collision, there may be binary mass transfer, mergers, etc. So it's the best way to identify the wavelength to which you can to study to get the flux from them. So I also studied something like, as I mentioned, when the sun becomes giant, it has to become cooler and bigger, right? It has to go to the other side of the Kalman diagram. But there are some stars which stay on the main sequence, continue to be on the main sequence, define the evolution. So initially people thought they are outliers, not part of the cluster, not member of the cluster. But then once you have the membership, we know that they are actually members, but they somehow are staying young, not following they have to go to the red giant because the core is collapsing and they have to become a giant. That's not happening. And we understand that they have gained mass after they are formed. So how do they gain mass? Is it binarity, or they merger, or what process is it? So that is they are called blue stragglers. So that is one of the aspects of what I was studying. So I was studying hot stars in globular clusters, because otherwise you won't find them, because they are very, very less luminous and near the center. It's very difficult to find unless you switch off all those lights from the other stars, which you can manage in UV, right? So these are the two other science themes. And so the theory what we came up with is you have two stars, A and B, sitting on the main sequence. Now they're together nearby, and when this becomes big, the other one takes the material through a Roche-Loeb mass transfer, and that star becomes bright. So it gains mass, and while this becomes a white dwarf. So this is a process of binary mass transfer happens. So these are blue stragglers are understood to be that, but people could not detect them. Now we detected them in UVIT. That was the important part. Second part is, are they all white dwarfs? So what is happening is you have two stars, like you have sun, let's say, and you have some smaller mass than that, and sun-like star is evolving. So at a point where the gravitational force is same, but there is a wind coming in, so the outside material gets channeled in through the Roche-Loeb through this star. So this gravitationally it attracts it and accretes it. So you are stripping the envelope of the star, right? So it's basically what I am getting is a stripped star. Is the stripped star equal to white dwarf? The formation of white dwarf is different because it actually lifts up the entire thing, and then only the core is left. They'll have a very thin atmosphere of hydrogen, but this may have a thicker atmosphere of hydrogen. So people did not understand it, and you can actually stripping can happen at any point. So it need not be actual typical white dwarf, you call it. So which people did not, unless you detect it, you can't even probe it, right? So we detected a handful of them. So this is how it works. Like you can have strip stars somewhere here, and this is the white dwarf. We did not know where the stars were falling. But now we ended up seeing that they are all falling in between, which we did not understand earlier. So that was another breakthrough which we had. So how do you do it? Like I claimed that I found companions, right? Like the star and the stripped companion. How do I find it? Because if it is going through a mass transfer, you'll have a brighter star and a hot companion. Now you can do it by, again, color-mantle diagram, the SED, which is basically nothing but a black-body curve. If this temperature of a star is it's 5,000 or 6,000 or 8,000, then you expect this will be its flux in the ultraviolet. But you detected flux will be, if it is higher than that, then that flux is coming from somewhere else. Then you make a combined flux for the entire distribution. Again, this requires multi-wavelength data, because you know for a particular temperature what is the flux at each wavelength. So you estimate that, measure that wavelength, and plot it over it. You subtract from the model. If nothing is excess, absolutely fine, it's a single star. But if there is an excess, you can have an excess in infrared also. That would mean that there is a cooler material around it. Like the young stellar objects, Bashwadi studies will have cooler material around it. It can re-radiate the stellar radiation in the warmer material, so you'll get an infrared excess. But if I have a hotter thing, not material, but generally you can't have except the corona case, but that's very small. But you have an object which is hotter near, you will get a UV excess. So we are checking the UV excess. That's how we check the we detect the companions. So there have been some results. I'll just stop here. So this is what we have found. So there were a lot of students who worked on it. There are a lot of clusters which we have worked on it. Totally we have, I think now it's not 17, it's 20 publications have come. And many people are working on it, not only me. Kaushar Vaidya from BITS and her students lead those papers as well. But a lot of students have worked on it. So what have we got? We have got some 20 20 clusters we studied. And you can see that this band is this band. This is low mass. So you can see that some of them come here, but many of them are coming in this band. So this is the band which is actually being populated, which is not known earlier. People thought it will come only in this band, and this is a gap. Gap is not there. It will be getting filled up. And there are many names in which people find. So that is one. Second is this another one where you would say that, okay, a star like sun will die as a planetary nebula. That's what the stellar evolution tells us. How many, if I have to understand stellar evolution from clusters, then you should see planetary nebula in clusters, right? Because that's how the stars die. So some dying star you should be finding in clusters, but we don't. And only one or two we know which has got planetary nebula, at least near the cluster. So why is it so? That's a question, because this phase of transitioning from here, which is as a giant, to become a white dwarf, which is this, is very short. So the time scale is very short, so you have to catch it in the act. It's very rare. And one such cluster is this, 2818, where this is the planetary nebula. If you look at the optical picture, you don't see anything like this, but this is the ultraviolet, because the star is exposing its interior by pushing it out. So you have all ionized material, which is actually bright in UV, so that's how you get it. So this is a very rare case of finding, and what we tried to do was prove it that this is part of the member of the cluster, which is also a problem. So we kind of made it. In the case of globular cluster, we had some, so this is the picture where you have this optical and the UV, so you can actually go and pick up the hot stars much easier, and the crowding is less. So there was a lot of science done with it. And this was some of the ASTROSAT discoveries where the UV was used to find galaxies which are emitting copiously, which was not expected in the cosmic noon. And these are from ultra deep surveys. These are led by Kanak Saha. These are other, I'm just giving you other results. There are a lot of results from them on the dwarf galaxies emitting in ultraviolet. So though this telescope, which moderate resolution and moderate size, have been able to pull out a lot of good results. And again, these are in no way in M31, which is actually, they'll come bright and go back, and that UVIT was able to identify them, and a lot of PhD theses come out of it. And this is the Cygnus loop, it's a supernova remnant, which is studied by Firoza and their group, but they're very beautiful pictures. But now we have to correlate what do we see with actual, what is the chemistry there, and which lines are being emitted. So this is the full region. And so these are the lines they are trying to do with X-ray. And there will be a lot of accreting binary sources which has been studied in the X-ray. There are a lot of binary X-ray sources. It could be neutron star or a black hole binaries, and they are variables, highly variable. So you need to have simultaneous data, and excellent data from LAX-PC, S60 and CZTI have done a lot of work. And these are X-ray binaries results. A lot of work from TIFR itself have come out. And these are timing and lines. And so you can talk to people about this. And X-ray polarization from SIG-X1 from CZTI. So that has been a major, there are all the gamma ray bursts which were observed from CZTI. So polarization also been detected. So there's a total summary of all the 10 years of ASTROSAT. Thanks to KP for this slide. So this is also produced from the ASTROSAT support cell, I suppose, in IUCAA. So these are the kind of studies which are done, and the publication category. And the summary is a lot of, So ambitious and very successful one, and payload has been functional for more than 10 years. It will continue to operate till it is technically feasible, and we're also looking at several follow-up missions based on success of ASTROSAT, etc. I wanted to actually stop here, but then I have one backup slide which Vandana wanted me to mention that I also have other, I wear multiple hats apart from being an administrator, but I also love Indian culture, and I also play violin, and just wanted to, I don't know whether the audio will work, but I'll just let me play a little bit of violin. I've performed in many forums, concerts and TVs also, mainly with my parents. I don't know whether it will work, let me see. It's not. It's working. So this is recorded as part of a movie which is called Yanam, which is part of the documentary, where there's also, after that, this bit sung by Dr. Radhakrishnan, who is the former ISRO chairman. This is part of, taken from Yanam, and that's a bit where I'm playing in. It's inside Kavalur telescope, one of the telescopes, so it was nice. It was a nice experience. I have gone to the telescope only for observations, not to play violin, but this was a different experience. Yeah, so what I want to mention is that, I still feel guilty that I don't practice much, but I try my best to do it. But what I'm trying to say is that it doesn't mean if you have some other passion, you should leave it and do it. It's, you decide what you want to pursue, but you do it properly. You can do it passionately. You can find time. It's just a matter of finding time, but you can always. But if you start saying that, oh, I'll do tomorrow, that's never going to come. That tomorrow will never come. And my father and my parents were musicians, and my father was singing. He passed away when he was 89, but he was singing till 88. 1 month before he passed away as such. Not even a single day he will miss singing. If you say, you didn't practice violin today, oh, today is gone. That's all he'll say. So if a time is 1 hour for me, 1 hour for you, everybody is the same. You can't win back the time. It's only up to you what you want to do with that time. Yeah. So I learned my hard lessons from them. And it's not, he never sang for someone, okay? It's nothing. It's not that he has a concert lined up and that's why he's practicing. No, there was no concert lined up for him. He wanted to make sure that he is happy with whatever he's doing. So that is him. So he doesn't, if something is wrong, it's wrong. Whoever it be, it's wrong. You have to fix it. So that's the bottom line. So, yeah. Thank you. So if you have any questions, I'm happy to answer. Not this part, but yeah. Anyway, yeah, I'll connect it again.
It was very nice that we could hear a bit of violin, at least here. It was really nice. So maybe you could say a little bit about what interested you in, how you picked up the astronomy.
Oh, okay. Yeah, so I grew up in a town I'm from Kerala. I grew up in Kerala, and when I was a kid, I come from, obviously, as I mentioned, come from a musical family. But they did not, my parents did not know whether what I was studying, and as long as I'm happy, they are happy. That's it. So the only thing is I have to practice. I took up violin, so I have to practice. That is the main thing. But I was sure that, there was a teacher next door who would give me some problems and excite me to, challenge me to solve it. So then it started with some challenge taken, and I'll try to solve it, which are, sometimes I won't, but sometimes I do solve. So it was quite nice. So he would give me tips, but he will not actually help me, but he will give me tips, so I have to solve it. So I found it interesting. Maths was interesting, and physics was interesting too. But then so physics, I eliminated everything, so I ended up actually taking physics. That's how I started taking physics. Rest of it was not possible, either music or physics. So it ended up in that fashion. But then I used to get up in the morning and study, and it used to be a very hot place. So I used to get up in the morning and study, and I used to look at the stars. And there's one more thing which used to happen was we had blackouts, like, the current cuts. So the current cut comes, you can't do anything, you have to go out and you look at the sky, and then started looking at the stars, and I became fond of it, and the sky was very good. And even in the morning I used to look at the Milky Way and look at the constellations. So, but nobody else was there, but we had Halley's Comet also at that time, so I was quite interested. So any opportunity to do anything with space, was very happy with it. So that initiated my interest. Yeah, so somehow managed to hang on to physics, and this also. The other plan B was always music, that was always there, yeah. So that's how I started.
Good evening, ma'am. Ma'am, as some like physics students, let's say we are interested in instrumentation, but we do not really have much, technical background. So how do we learn about it or get into it, and how can we, how difficult is it for us?
No, see, actually, I did not have any basic thing. Basic training in instrumentation. But whatever we do, we used to double with it. Like we had laboratory, BSc, MSc laboratories used to be there. No, we used to be in government college. I studied in government college, and nothing used to work. So for bachelors we had a teacher. As a teacher, he was not great to give a lecture which would be motivating, but then he would motivate us in the laboratory by saying that if something is not working, tell me why it is not working. If you have a potentiometer, if it is not giving you the actual value of, you cannot balance the load or whatever it is. If it could be Young's modulus experiment, you're not able to measure the Young's modulus and give you the value, right? You actually fudge the numbers. He would stop us from fudging the numbers and say, you actually write down whatever measurement you took, and write what is the possible reason why which it's not work, you're not able to get the readings. So he actually challenged us to think about it. So it was an eye-opener, and used to be another one. So what I'm saying is, it's not that there has to be unmeasurable resources for you to actually understand. No, there are right things in front of you, you can question and understand. And my motivation to start continuing with physics was absolutely this optics experiment. Something would not work. We used to spend time, stay back, and find out the reason why it is not working, or at least to say this much we can get, beyond which it may be due to so and so and so and so. Used to be one experiment where we have a lab book. Potentiometer has this 10 lines, right? And that experiment diagram will put only 4 lines. So we copy the entire thing and put in the record 4 lines. Because that's how it is written in the guidebook, right? You put it. He will refuse to sign. You say, that person drew 4 lines and you are copying it. 4 is not correct. If you want to do it properly, draw 10 lines. Otherwise, draw 1 line symbolically. So you're not even paying attention to what you're doing. So ask yourself what you're doing. So every time we had to take up an experiment, it used to be initially a headache, but it turned out to be pretty good later on. For every experiment, we have to understand, or at least convince ourselves. They said, it's not me who is asking for demanding the answer, you convince yourself. So a few of us were very enthusiastic about those questions, and we chased it up. And error analysis was not even there in our syllabus or anything, but we actually tried to understand what does it mean, how does it add up. So experimentally, we could actually understand. So it's not about there are enough things around you, we can actually question it. So the most important thing is you start asking yourself questions, and that will lead to a lot of understanding. Of course, if you get an opportunity, that's nothing like it. I've never seen a telescope in life till I came to IIA, but that isn't, so asking the right question and developing that habit helps you in any situation. I don't know whether I answered that question, but it's important. Yeah.
Ma'am, from being a student like us to being the director at IIA, you must have faced a lot of challenges. So what is that one memorable challenge that you faced and how you overcame it?
Sorry, I can't remember challenges. So I see, the thing is, like, there would be many fights, and I'm not a person who would like to remember fights, because if I start to remember the fights, I would remember only the fights. I would keep only my, I'd like to think only about what things I have to do and how it helped me. So I have trained my mind to forget things which I don't want to remember. And the only way to do that is not to remember, forcefully not remember. So yes, of course, there are a lot of challenges. But I don't want to be remembering about the challenges, yeah. I would like to focus on getting to what I want to do, not getting
Ma'am, is there a story related to any project that you worked on, or mission that you worked on related to technology or the space missions?
Yeah, so UVIT is something which, like, when I started working on it, people said you don't have any experience in working about UV. Forget about any experience, don't have any experience to begin with. Second, you don't have any experience working on ultraviolet, because I worked on optical all the time, but I understood what calibration meant. And second, I don't know anything about space instrument. We never had any space instrument for that matter. So people said, you don't have experience. I said, fine, doesn't matter, let me learn. Somebody said, no, you already have done and everything is done, you are starting refresh. I said, doesn't matter, let me repeat it. So I started working on it. There are many things which are unknown. But then nobody there knew it, right? There was nobody who would know it. It's not that somebody knew everything, and still you have to find it yourself. There's no other go. So you take it up and do it. But the only thing is you have to be honest about it. You need to decide whether you understood or not understood. And working with people like Shyam Tandon was extremely challenging, because it is not easy to convince him of your ideas. So, but that doesn't matter. But once it is convinced, you actually know you are completely 100% or 200% confident about what you're doing. And there would be lots of challenges. But if you don't understand, you have to say, okay, you don't understand, say, take a step back, come back with that. And if there's a setback, you don't collapse and crumble there. You have to understand what went wrong, go back, fix it, and come back again. There's nothing wrong. So that confidence, you can do it, and you should do it. And there's nothing, there'll be downtime, but it doesn't matter. You just get up and start doing things. You have to. The main thing is to your idea is to reach the focus. So don't get distracted by all those noise. There'll be a lot of noise. Don't get distracted. The thing is to go there, the focus, yeah. And I also was working on TMT. So the TMT had a challenging project also. So daytime I used to work on TMT daytime for ASTROSAT and nighttime for a TMT software. We used to defend it because it was there in the US. So you will go through challenging times, but the most important thing is it's difficult, no doubt about it. But once you do it, you're not the same person anymore. And that experience, you will get that experience only by doing it, and you can't escape it. So if you want to have that experience and you have to have that capability, you have to face challenges. There's no way. Any science question? Yeah.
What do you mean by the LMXBs with neutron stars?
LMXB is a large X-ray proportional counter work with neutron stars. So low mass, sorry, LMXB. So it's not LUXPC, sorry, low mass X-ray binaries. So X-ray binaries are, you have a binary which is detected in X-ray. Now you can have the X-ray production based on the accretion disk around it. It could be a low mass X-ray binary or a high mass X-ray binary. So these low mass X-ray binaries are low mass systems normally found with old systems. So the secondary which is there is actually a neutron star, but the secondary which is feeding in this generally could be a low mass star found in globular clusters kind of thing. There can be HMXBs, which are high mass X-ray binaries, where the neutron star, more massive neutron star, and is fed through a high mass star, which is normally thought to be a young system. This is an old system, and energetics are also different. So LMXB's energetics will be different from HMXB's energetics. But these are binary systems where one is a compact neutron star, the other is a star, which is feeding it. The accretion disk is fed by the other star. Yeah.
Can there be any other mechanism than mass accretion from the companion that can lead to the formation of blue stragglers?
Yeah, so you can have mergers of stars because you have two binary stars which are going together. So they can merge through, it's called there will be a lot of matter which would be ejected out of the system, angular momentum will be taken away, but they can eventually merge. But how do you know there's a merger system or an accretion system? So there would be signatures like you have to find a companion's mass, then based on the companions, the strip star's mass, what evolution it has gone through, and has it accreted processed matter. In an asymptotic giant branch star, you'll have processed matter coming in, S process elements. Is it got that? So like that, you'll have to probe multiple levels. So right now we are probing not only about binarity, so you need to find it's a binary system. So and then what is the period, what's the orbital period, and what is the mass of each component, and then you actually go back to MESA and model it and find out how exactly it evolved, etc., etc. So if there is only one star there, then the companion is not there, then it could be a single star. But then you can track its binarity, it's single line spectroscopic binary, small object going in, so you can actually get it. If there could be large periods there, but we haven't yet convincingly found a system where, yes, it's a merger output. There can be, because in M67 where we studied, we have binary blue straggler. Two stars which is in a binary system, both are blue stragglers, which would mean that it has to come from a quadruple system or something like that. So we really don't know. And this is not a case like a globular cluster where this kind of a collision will be there. This kind of generally is a spiraling in. So how they merge is also different from globular cluster to here. So, but we haven't come across a star and prove it that is exactly a merged one. Yeah, not yet.
Also, ma'am, have you found any cases or have you linked the formation of blue stragglers to any of the specific origins of these stars? Like specific origins of the stars that are causing blue stragglers?
It's basically binary systems are combined because you do find a large fraction of binaries among blue stragglers, and you also find a link with algol-like systems. So connection between blue stragglers and binaries are established. Now, how they become blue straggler by mass transfer or by merger, like spiraling in, we are not yet. And there are also role of tertiary systems where you have three body system where the third one actually takes away the energy and then it shrinks the orbit of the inner binary, which helps it to merge. So those systems are also found, but difficult to characterize them because if you look at the radial velocity variations, you cannot convincingly deconvolve the triple systems. It's not easy.
Thank you.
I have one question.
Yeah.
What is the position of that ASTROSAT that you have kept? Which Lagrange point, like specifically?
No, it is in a low Earth orbit, 650 kilometers.
Okay, so
ASTROSAT
it doesn't have to be on like L2 place?
No. That L1 we will not put at all because it's between Earth and the Sun. That's not the right point. The point will be to L2.
Okay.
Same 1.6 million kilometer away on the other side. Yeah. That's where other mission like Kepler may be there, Gaia, JWST.
So why specifically like lower Earth orbit was chosen for that?
No, low Earth orbit means you can launch and operate operational things. So we haven't yet launched anything to L2 so far. L1 is the first one which Aditya went, and most are either LEO orbits or GEO orbits. GEO orbits are generally the communication satellites where it has to be seen, communicate with it. L1 or the LEO orbits will be like 90-minute orbit typically. So it will be going around so many orbits, 18 orbits per day.
Okay, so doesn't the Earth's light interfere in the observation of?
No, you do. So you have to imagine this is the sun, I'm the Earth. It will go around like this. Yeah. So when it passes through the sun, that time there won't be observation. So in the 90-minute observations, the satellite can be looking anywhere. It can look at here also. But when it comes to, this is the night side, right?
Yeah.
So Earth is blocking, it's an equatorial orbit. So if it comes, UVIT will be observational only 1/3 of the orbit.
Okay.
So once it crosses the delimiter point, the detector voltages are in the standby mode. Then the high voltage increases one by one by visual NUV, FUV will come. Observation will start. Again, delimiter stop. The high voltage will go to standby mode. Then it will orbit again.
Okay.
And it has to see the sun because solar panels have to be charged.
Okay. Thank you.
But other things are always up.
Okay.
Other instruments. Only UVIT has a problem.
Ma'am, as you mentioned that in ground-based observatories, the shape of antenna depends on the according to the energy of the photons we are collecting. So how does it vary in different regions?
Oh, it's not even shape. It's material also very changes. You start from optical to is glass, and you don't need glass for these things, right? So it's not only about collecting the photons, detecting the photons. Everything changes. So first you have to collect the photon and bring it to a focus. Collecting is also changes, and bringing to focus, and then you have to sense it. Then also it changes. So it's a wide variety involved there.
And ma'am, also you mentioned about simultaneity of data in like
Yes.
How does that is achieved in the satellite?
Yes, in ASTROSAT everything points to the same direction. Everything will have similar different field of view. I mean, someone will look at it like this, someone will look like this, someone will look like this, but they're all co-pointed.
Okay, thank you, ma'am.
Hi, I remember there was a conference recently on the 10 years of ASTROSAT.
Yes.
I'm sure you were there. Could you tell us about any, really significant or surprising or unique results people presented?
I mean, I just picked up some of the results, but many of them are very interesting results, and they have been, it's not like at 10 years people produce the results. The results have been coming out at constant intervals. 10 years is basically bringing all this together like a picture here. This probably is the 10-year data kind of a thing. So how many publications, which are the areas you looked at. So significance things are like, I mean, what I mentioned, like detecting formation pathways of blue stragglers and end stages of low mass stars, what I have studied. But in Kanaksaha's group, they have studied galaxies which are leaking Lyman alpha photons. So they were UV bright, which we didn't think that UV detection will come at all. And there were some galaxies which are actually merging. We have studied some galaxies where a galaxy is falling into a cluster, and the gas is getting, it's pushed away by ramp pressure. And those gas actually can condense and form stars. And those galaxies are called as jellyfish galaxies. So those star formation we actually studied in UV in combination with H alpha. And there were studies on, these are UV studies, but of course gamma ray detections by CCTI. There were also timing, there were a lot of timing estimations of certain types of flares and LMXPs and neutron star binaries, black hole binaries. Many things are done. And also, we also combine the data coming from UVIT with other missions also to make it multi-wavelength. So there were lots of results, yeah. All the instruments together. And there are also science results which combine to study the AGN, which is a multi-wavelength data from ASTROSAT itself, to find out what are the energetics coming from there, what is the process by which the AGN is actually flaring, etc.
Also, I saw that all of the data collected from ASTROSAT and everything is publicly available. You also have really good tutorials for data analysis for all of these different softwares.
Yes.
Could you suggest any, short data analysis projects all of us could work on, like whoever is interested could work on, using these tutorials and publicly available data?
It's possible. There's a lot of tools which are available and a lot of data is available, but what you need to have some science themes as well. You can't just randomly pick up and do it. You'll have to. There have been ASTROSAT Science Cell have been organizing workshops where they also group people into various projects and then actually get them do it. You need some resources because someone to help you out with this thing. So it has to be planned and executed. You can't just say, okay, let's work on something. But it's possible, and there have been workshops as well. It's a good idea, yeah, to continue to do it, yes.
Okay, so I think you can thank Subramaniam for his wonderful.
Thank you.
Cycling of voltages of this UVIT, like this is automated, right?
No, no, no.
They do it by
Initiate.
hand.
What
No,
cycling?
like this.
Yeah,
that is
automated.
automated.
Yeah,
Because it's just a part
no,
of
it's a
the
delimiter also. Yeah. That's part of.